Hello everyone, we'll go ahead and start our standard 2 video here. Unit 1 in Statistics, Standard 2, focuses on identifying, creating, and interpreting categorical data displays. First off, we'll start with talking about the 5 W's of data. Data is measuring the 5 W's: who, what, when, where, and why. And oftentimes how the data is collected is also relevant. Is it collected voluntarily, or are participants selected at random? Is the survey anonymous, or are the participants required to submit their name? Might skew their results. Obviously, not knowing the first two, who or what, would make the data meaningless. Who is known as the population, which is oftentimes a sample of the larger population. So in statistics, we have what's called a sample and population. So let's call this set the population. Well, it's oftentimes too time-consuming and expensive to ask everyone, so what statisticians do is they take a sample. I could ask everyone in this sample. I can ask everyone in this sample, or this sample, for the overall population. And we conduct statistical inference to see how closely or accurately the data from our sample reflects the overall population. How much confidence do we have that our data from the sample reflects the overall parameters in our population? Like we talked about, which is oftentimes a sample of the larger population. What are the characteristics we're measuring about each of the samples collected? These are known as the variables. Variables are either categorical. This is when the variable names a category and answers questions about how those cases fall within those categories. So a good example of a categorical variable, eye color. We ask our participants about what color their eyes are, and they respond with either brown, blue, green, gray, etc. Oftentimes, a categorical variable is where the answer isn't a number. Rather, it's a name. What state were you born in? Minnesota, Iowa, Illinois, Wisconsin, Nebraska, etc. Next, we have a quantitative variable. A quantitative variable is when a variable measures units about what quantity we're trying to measure. So for example, we could talk about your weight. How many pounds or kilograms do you weigh? What's your height or your shoe size? Inches, etc. Quantitative refers to a quantity. So when what we're trying to measure can be answered with a quantity, a number, this is a quantitative variable. When, where, and for what purpose the data is being collected is also very useful. These determine how relevant the data is. So when it comes to when was the data collected? How recent was that data collected? The more recent, the better. Where was the data collected? Why was the data collected? For what purpose? For what purpose the data is collected might come into some source bias. The people who are doing the data, collecting the data, do they have any purpose? Are they trying to show something to be true? Oftentimes we can make statistics prove whatever we want to prove. So it's always important to understand where the data is coming from and how much faith we have in the numbers we're being presented. How the data is being collected. We also talked about this a little bit earlier. What sampling method was being employed? Was our study collected anonymously? Did we use random sampling or convenience sampling? I want to have my sample data be as representative of the overall population as possible. So typically, random sampling is a better alternative to convenience sampling. It's best to ask every 10th person than to ask only the people who are interested in responding. Random sample versus sampling done for convenience. So here on this slide, I have a little snippet here about some Tour de France results. For this picture, let's list as many of the 5 W's as we can and classify each variable as either categorical or quantitative. If the variable is quantitative, what units is our variable being measured in? So reading below, we'll do the best we can here. It is kind of small. In the 2003 Tour de France, Lance Armstrong averaged 40.94 kilometers per hour for the entire course, making it the fastest Tour de France in its 100-year history. In 2004, he made history again by winning the race for an unprecedented 6th time. In 2005, he became the only 7-time winner and once again set a new record for the fastest average speed. You can find data on all the Tour de France runners below. Here are the first 3 and last 10 lines of the data set. Keep in mind the entire data set has nearly 100 entries. So here we have year, winner, country of origin, total time, average speed, stages, total distance, starting riders, and finishing riders. Each of those columns outlines the who, what, when, where, and why, some part of that. So the who, they would be Tour de France race winners. The what, well, that would be all the other columns. Here we have our winners, and what we're measuring about those winners would be the year 1, country of origin, the total time, the average speed, the stages, the total distance ridden, the number of starting riders, and the number of finishing riders. Those would be our what, our variables. Which of those variables are categorical? Which of those variables are quantitative? The only categorical variable would be the respective country of origin. What country was the Tour de France winner that year from? France, Italy, Spain, Argentina, etc. The other variables are quantitative. Now, obviously, years, there is some discrepancy. It kind of depends on what you're trying to do with this data, but typically year can either be quantitative or categorical, since it's not really a continuous data point. We'll call this quantitative, just to kind of stick with the overall theme of if it's a number, it's quantitative. If it's anything else, it's categorical. So year would be quantitative. The total time is a quantitative variable measured in hours, minutes, and seconds. The average speed is a quantitative variable measured in kilometers per hour. Stages 1 is a quantitative variable. Total distance ridden, quantitative, measured in kilometers. The number of starting riders and finishing riders are also both quantitative variables. Where was this data taken? It's a Tour de France, so maybe it was taken in France, since that's where the race is being run. When? Well, that would be between the years 1903 and 2008. Why? It doesn't really say. Maybe they're trying to study the history of the Tour de France. Maybe they're talking about advancement in the science of cycling or the science of human endurance. We can see improvements in the overall speed and race time and distance, given the data below. The next couple slides talk about different representations of categorical data. Categorical data can be represented in a tabular representation, below with what we call a frequency table. A frequency table records the overall count of each category within a table. So here we have our variable, which would be post-secondary degrees. And our participants respond with either high school, bachelor's, an MBA, master's degree, law degree, or PhD. So you can see in the table, there were 40 different. Get that out of the way there. There were 40 different participants. 2 of them had a high school degree. 7 of them had a bachelor's degree. 20 of them had an MBA. 3 had a master's degree. 4 had a law degree. And I believe 4 also had a PhD. A frequency table records the frequency or count of each of the respective responses across the distribution of a categorical variable. We could also have a relative frequency table. A relative frequency table records the proportion of all responses that fall into each category. So for high school, we see 2 out of 40, or 0.055%. For a bachelor's degree, 7 responses of the 40, 7 out of 40, or 0.175, 17.5%. MBA would be 20 out of 40, 0.5 or 50%. The proportion of responses that had master's degree would be 3 out of 40, 7.5%. Law degree and PhD, 4 out of 40, or roughly 10%. The nice thing about frequency tables is I can quickly see that a large amount of our responses, half of them, had an MBA. Not many of them had only a high school degree, only 5%. Another tabular representation of categorical data can be done with a contingency table, otherwise known as a two-way table. A two-way table can display the interrelationship for 2 different categorical variables. Used for conditional distributions to show distribution of one variable for just those cases that satisfy a condition on another variable. So using the table below, we have 2 different variables. The rows, our variable is gender, males and females. And we're recording the number of either males or females that said that their favorite sport to watch on television is football, basketball, or baseball. So I can see that 40 males liked football, 22 males liked basketball, 15 males responded that they liked baseball. In the next row, 12 females liked football, 16 females liked basketball, and 45 males liked baseball. What's nice about this is I can see how the 2 variables relate to each other. Is there any correlation or correspondence between gender and favorite sport? So we can pretty easily see, based off of our sample, that a large amount of males prefer to watch football. However, a large amount of females prefer to watch baseball. Another good part about contingency tables is when I don't have an equal number of responses for the different categories within our variable. I had 40 plus 22 plus 15, that would be 62 plus 15, 77 males. Let's see here, 12 plus 16 would be 28 plus 45. 45 and 28 would be 73. I have a different number of males and females that respond, but I can still kind of break that apart to see the interrelationship between gender and favorite sports on television. One disadvantage of a contingency table is it doesn't take into account any other variables that might have an impact on gender versus favorite sports. What about geographic distribution? Might be interesting to see where these males and females were from. You know, baseball might be more popular in certain parts of the country than others. Same with basketball or football. That could also kind of skew or misrepresent our data. Okay, so here's some practice. Let's take a look at what parts of our sample are given in the two-way table or contingency table below. Calculate some probabilities. What parts of the sample do each of these questions describe? So for question 1, what percent of colds lasted between 1 to 3 days? So looking at the table, I see that there are 200 different responses. 1 to 3 days, that would be the top row. So in total, there were 105 colds out of the 200 grand total that lasted between 1 to 3 days. So 105 out of 200. out of 200. So as a percent, that would be 52.5%. 52.5% of our sample had a cold that lasted between 1 and 3 days. What percent of colds do patients not take medicine? Well, out of the 200 grand total in our sample, how many colds did not take medicine? That would be 98. So 98 out of 200 as a percent, that would be 49%. Question number 3. In what percent of colds lasting 4 to 7 days do people not take medicine? Now read carefully here. We're restricting ourselves to only look at colds that last between 4 to 7 days. So I can only look at this row here in the middle of our table. Out of the 95 total colds that lasted 4 to 7 days, in what part of those did people take medicine? 16. So 16 out of 95. So let's see here. I might need a calculator for that. 16 out of 95 is roughly 16.84%. Number 4, in colds where no medicine was taken, what percent lasted between 1 and 3 days? In colds where no medicine was taken, what percent lasted between 1 and 3 days? So out of all the colds where no medicine was taken, so that would be in this middle column. So that would be 98 total colds where no medicine was taken. What part lasted between 1 and 3 days? That'd be the 19 here. 19 of 98. Get a calculator for this one. 19 of 98 is roughly 19.39%. I think we had one more. What percent of all colds lasted 1 to 3 days in which the patient also took medicine? Now, what is our overall total? What percent of all colds? Well, all colds means we're back to our 200 grand total. Now, I'm only looking at the colds that lasted between 1 and 3 days where the patient also took medicine. So that would be out of the 200, 1 to 3 days, also took medicine. At our table, that would be 86 out of 200. And 86 divided by 200, or 43%. All right, we got some tabular representations of categorical variables. Let's look at some other ways to represent categorical variables. Graphically. A couple good examples of some graphical ways to represent categorical variables would be in a bar chart. A bar chart displays the distribution of a categorical variable, the different responses, where we show the counts for each category next to each other. So a couple different examples of bar charts. I'm sure we've all seen these before. Our variable would be the colors in a bag of M&M candies. Could be green, red, yellow, blue, orange, and brown. And we display the frequency or count of the number of candies in the bag over here on the y-axis, the vertical axis. Another example would be favorite movie genre. You could have either comedy, action, romance, drama, sci-fi, etc. And then over here on the vertical y-axis, we display the frequency of the people in our sample that preferred those types of movie genres. What are some advantages and disadvantages? Well, they're easy to read. We can quickly see what was the most popular or least popular, most frequent or least frequent. It kind of depends on the bar graph, but in the one here on the left, I'm not really sure how many brown candies there were. It's kind of in between the 20 and 30. 25, 28. I'm just estimating. Yellow candy's the same way. Less precision, less accuracy when we don't have the actual raw data. Another example when it comes to disadvantages. What if I played around with the scale here? So rather than from 0 to 10, it just went from 0 to 20. It would skew the overall heights of the genres of movies, might make it so that one movie appears to be more preferable than another. By playing with the min and max of the counts on the y-axis, it might disperse or skew our bar graph. Lastly, here we have a pie chart as another way to display categorical data. So we show the whole group of cases as a circle. We display the entire distribution as a circle, and the circle is then sliced into pieces whose sizes are proportion to the fraction of the whole. The proportion of cases that fall within each category of the variable. So here we have a pie chart representing social media engagement. What percent of time is somebody spending on each of these relative sites? Facebook, Twitter, Google+, LinkedIn, Tumblr, and Pinterest. So we can see quickly that Facebook represents a pretty large proportion of the time that this person spends on social media. Also see that this slice of the pie, I believe that represents Google+. Less so when it comes to Tumblr, Pinterest, etc. Advantages, once again, everyone's pretty familiar with pie charts. They're easy to read, and it's quickly able to figure out what's the most frequent and least frequent response for the categorical variable. This pie chart's pretty nice in that it gives us the count and relative frequency. 13, which accounts for 27.7% of the distribution. They don't always all do that, so that would be one drawback. This had 6 categories. What if I included more social media, like, for example, TikTok or Instagram? The more categories I have in the distribution, it might make my pie chart a little bit less legible, as it kind of gets smushed in there and hard to read. Believe that takes us to the end of the slides here. So hope this helps. Have a great day.